Oh shit, it's recording. I can't explain nukes anymore, guys. I'm sorry. Next time. Next time. Next. Okay. So today we will be doing well, some analysis. Not exactly. We'll be doing like a very specific thing in analysis because once again, general analysis is important for later classes. So yeah. Also, since it's just start recording, happy Diwali again. Hmm. So the main question we'll be trying to answer in this question in this lecture is given a function R to R considered a set like, let's call it C of F. Yeah, C for continuity to be X in R such that F is at X. So all the all the real numbers at which the function F is continuous. So the answer is the problem is classify all possible CF. Okay, so before I start, how many people here know the epsilon delta definition of continuity? I'll be covering it, but just to get an idea, just raise your hand or type in chat. Okay, no, no. Okay, just one person. Okay, that's good. That's is the writing pad still in repair? I am writing with the writing pad. Oh my. Okay, please understand.
Wait, you are writing with writing part?
My handwriting is just this bad. We had a group project here in college, and like I wrote my half, and like my teammate was like, "Bro, this like please rewrite this. This no one will understand what this is." Yeah. Okay. So anyway, so here's what about the people who already know the epsilon delta definition. Start trying to answer this question. In fact, wait. Let's make it clear. Uh oh, Paris, isn't there also a Sophie class? Why are people here?
It's at
We are
7.
I think there, I don't know. College Imperial College then. Anyway, so we are doing analysis, and the problem that we will do this lecture is take an F real to reals and call CF to be the set of all real numbers at which F is continuous. And we want to classify all possible CF. So people who know the epsilon delta definition of continuity, you can start with this. Is it possible that a function is continuous at the rationals and only at the rationals? So like can Q equal CF? For the others, I'll formally define what continuity is. Okay. So people who like, can someone who like doesn't know the epsilon delta definition, like just say what they think continuity is, like unrigorously?
Seriously, it should be like that. I mean, should epsilon should be very small.
Epsilon, don't mention epsilon and delta, but okay, yeah. It,
Isn't it
like
like limit exists?
limit exists, yes. It is limit exists, but then okay,
And
epsilon
f
It
delta
is
equal to
definition of
limit.
limit.
differentiable.
And f of a is equal to limit at
But
like
then that's the correct definition, but then like you shift the burden to defining what a limit is.
bro, that's like
It's like okay, give a formal definition of a limit then. Graph shouldn't cut. I don't know epsilon. Okay, okay. So
isn't limit defined using epsilon?
okay, so yeah, limit is defined using epsilon. I'm getting to it. Isn't there a Sophie class right now? What is happening? Why are Sophie students here? Oh, it's
It's
inequalities.
at
Ah,
7.
okay.
It's at 7. It's at
Oh, it's
7.
7. Ah, okay. Huh. Anyway. Yes, so okay, so I'll give you some people some idea. Mm, but yes. So this everyone would agree is discontinuous at this point. You're doing analysis. I beg, please be rigorous. Yeah, I am defining epsilon delta. I will be defining everything rigorously. The people who already know the rigorous definitions can start working on the problem. Like I'm slowly motivating the rigorous definition for the benefit of the others. Anyway, so wait, okay, let's start with to motivate epsilon delta. Maybe I should start with sequences. Okay, so before okay, okay, fine. I'll repeat. I'll repeat. There's a function real to
Can
real.
you like tell the problem?
Yes. So the problem you can work on, if you know epsilon delta already,
But like
f be
what?
a function R to R. We call CF to be the set of all real numbers x such that f is continuous at x. So the set of continuity of f. So, well, the main question we will answer in this lecture is we will classify all possible CF. But the question you should work on right now is, can Q be CF? Can there be a function that is continuous at all rational numbers and at only the rational
Like
numbers?
is this a specific function or a general function?
Is no, is there any function that can have Q as its
Okay.
set of continuity? Find the construction or prove doesn't exist. The normal stuff. Anyway, okay. So first, before I define continuity, I'll like define limits. So take this. Let's say 1/2, 1/3, 1/4, and so on. Uh, you would agree the sequence approaches 0. Everyone would agree that, right? Every number gets smaller and smaller. The question is, how can we say that like rigorously? So one way you could think of is the distance of this function from 0 keeps decreasing, right? Like for like not this function, the sequence. So at first it's at distance 1, then it's at half, then it's at 1/3, then at 1/4. So since the distance keeps decreasing, it gets closer and closer to 0. But why is just saying that not enough?
Because
Like
like
just
distance could keep decreasing and could approach a value that's like not yet
correct. Yeah,
zero.
yeah, yeah. So the thing is, this sequence also gets closer and closer to -1, but you obviously won't say that the sequence approaches -1, right? So we add a second restriction that we say a sequence approaches a limit, say x, say L, if it gets closer to L and it can get as close as you want. So for -1, like the distance of any of these numbers from -1, it will always be greater than 1. But for 0, it will eventually get very small, right? Smaller than anything you can like ask for. It will get smaller than any positive real number. So here's what so and that is the definition of a limit, basically. So take a sequence, A1, all like okay. Just okay, sequence AI. We say that AI approaches like it is nice motivation though. Thanks. We say that AI goes to a limit L as I goes to infinity. This notation is like whatever. You will write it as limit I goes to infinity, I don't care. Yeah, we say AI goes to L if so we want the distance to become as small as possible, right? So the way we will say this is it can become smaller than any positive real number. Is that for all epsilon greater than 0? And you should think of epsilon as being some really small real number. So, okay. So suppose we want this to get like this sequence. It's approaching 0. We want it to be within 1/5 of 0. So it doesn't start by being 1/5 of 0. But eventually it will be within 1/5 of 0. Right? So we say there exists some capital N such that so like any member of the sequence after capital N, like after a capital N, is within epsilon of the limit. Does this definition like make intuitive
Oh,
sense to everyone?
okay.
Uh,
Like suppose like there is a sequence
Hmm.
which gets arbitrarily close,
Hmm.
but it's like fluctuating up and down. For example, like at one point it's very close, but at the second point it is like very high. But like
Yeah. Okay.
you can always get it as close as you want.
Yes.
But
Yes.
it's not
Exactly.
like
That
that
I should have
I
mentioned
is
that.
equal to n for
Yeah.
it or
Okay.
like
Yeah.
zero.
Yeah.
can
Go.
you could you somehow repeat from the
So
beginning? My
would
network is
that
extremely
like
bad.
be called a limit or not?
Yeah. Sanskar, you're correct. So wait. I'll come back.
Yeah, can you somehow repeat from the beginning? Like my network is actually bad. I couldn't
Uh,
hear.
okay. Okay. Sure. Sure. Okay. So I'll repeat. So what we are trying to do. We are trying to define what a limit is regressively, right? So here's like the things we want. So first, our intuition says that if we take like this sequence, 1/2, 1/3, 1/4, then this should approach 0, right? So what kind of
Yes.
conditions do we want? Well, we know the sequence gets closer to 0, but the sequence also gets like closer and closer to -1. So what we really want to say is that this sequence can get as close to 0 as we want, right? Like for any real number, the sequence will be for any positive real number, the sequence will get like at a smaller distance from 0 than that real number. Like pick 0.0001, this sequence will eventually be closer to 0 than 0.0001, right?
Yeah,
The
makes
second thing
sense.
is, suppose like take this sequence, like splice ones in the middle, right? So like
Okay.
it goes to 0, but it keeps jumping up. Now we won't say that like this approaches 0, like intuitively. This doesn't approach 0. This keeps fluctuating between like close to 0 and 1, close to 0 and 1. So what our definition should say is that the number gets as close to 0 as we want and stays there, right?
What's like stays there?
Like it doesn't like fluctuate back up to 1.
Okay, like it stays closer to 0.
It stays closer to 0.
Okay.
So like the way we regress this is this. So take a sequence AI. We say that ignore this notation. This is like definitely not correct notation, but whatever. We say that AI, the sequence, approaches a limit L if for any positive epsilon, the sequence will eventually be closer to L than epsilon. So there exists some n, like n you can think of as like some point in the sequence, such that for all AI after this, for I should write this as this, for all I that are bigger than n, AI and L are within epsilon of each other.
Okay. Okay,
Right.
yeah, makes sense.
Right. So like suppose this is the limit, then like this is the real number line. Sorry to interrupt, but you didn't define a sequence formally. But just a function from n to r or c. A sequence is a function from n to c. Please, please, like come on. That's stupid, antic, bro. Yeah. So yeah. So basically, the way you should think about this is like a sequence like it's somewhere here, it's somewhere here, it's somewhere here. But like for any interval you draw around the limit L, the sequence will eventually come inside this interval. It might leave, then it can come back inside. But eventually it will just come inside and not leave it again. Right? Because if it eventually it will just come inside this box and stay there. Is that clear? Is this definition of a limit clear to everyone?
Yeah.
Yeah. If someone still has any doubt about like either the motivation or what like the symbols mean, you can ask. Otherwise, I'll move on.
I have one question, which is that,
Yeah.
uh, as you said, for all epsilon, there should exist an AI such that it's
Hmm.
epsilon, its difference is less than epsilon. So,
Wait.
by definition, a limiting sequence must be continuous, right?
We have not defined what continuous is yet.
Okay.
Like, continuous is defined for functions, not sequences. Right? How do you solve the fluctuating issue? Yeah, the point is I demand that for all I greater than equal to n, ai minus l is less than epsilon. So like for this sequence where like ones are spliced in the middle, like for no matter what n I pick, at some point after this, the function will be 1. And like 1 minus 0 is not less than epsilon. Well, assuming you have picked the small epsilon. Like, this is what I did. I demanded that the sequence should be closed for all I after some point. Anirudh, is that clear?
Yeah, but in this fluctuating thing, it is not.
Yeah.
Wait,
Okay.
like what if the fluctuations are decreasing? Like for example,
Ah,
after this, one becomes zero point 0.5 and then one becomes like 0.25 and so on.
then it's fine. Then it's
Then the
fine.
limit would exist, right?
Yeah, then the limit would exist because like Even if it's like going up and down, it's like slowly coming closer and closer to zero and staying there.
Yes.
It doesn't have to monotonically go there. It can like go up, go down, go up, go down, as long as it is going there. Okay.
If epsilon is
Okay.
0.5 and if it reaches 0.4 at some point and then goes to 0.45,
Yeah.
then wouldn't that be an issue?
No, that's fine as long as it comes back down to 0.4 and stay. Like it goes down, then it goes up, then it goes down, then it goes up. But as long as eventually it stays below 0.4, it's fine. And
When epsilon is 0.5, then
okay.
if it like goes 0.41, 0.411 and
Okay.
so on, then there would be an issue.
Okay, epsilon is 0.4.
0.5.
0.5, okay. Yeah.
And then it reaches 0.4 at some point, then it
No,
increases to
no, epsilon
0.4.
is not changing. What are you saying?
No,
Function.
the
Yeah, yeah.
value you get from
The
the
sequence.
I mean the next term in the
Okay,
sequence.
so the sequence is like 0.4, then what?
Then 0.41
41.
and it increases, but it's still but epsilon is still sorry, but the value is still lesser than epsilon. The difference is
Yeah,
still epsilon.
this is fine. This is fine. Like, the point, this doesn't have to be true for some particular epsilon. This has to be true for every possible epsilon, right? So even if some epsilon satisfies this, like some smaller epsilon might give a contradiction, and then the sequence is not converging.
Okay, okay, got it.
The epsilon is okay. No, technically, I said for all epsilon greater than 0. You can pick epsilon equal 10 to the 100 if you want to. Every epsilon should work. And like clearly, if any epsilon works, then all epsilon larger than it works. That is why you always only pick small epsilons, but nothing's stopping you from picking a large one. Okay. Now we will generalize this to a limit of a function. So for a function, now we no longer have a sequence, right? We have an f r to a, and we want to say like limit x goes to say a of f of x is L. How do we like use the above definition and try to guess what the definition will be here?
The limit of the sequence, like f of
Mm,
uh, a minus something and like getting close to 0.
I mean, you can define it using sequences, but I prefer the other way.
If after like a certain point, if after like a certain value of the inputs,
Hmm.
the function reaches closer and closer to n. And based on
Yes.
epsilon, as epsilon approaches like 0, the function approaches n, something like that.
Yeah. Okay. Yeah. So earlier we had like a discrete sequence, but now we have a function. Do by any chance x minus delta greater than? Okay, I'm not sure what you're saying, but yeah. So the point is, what we want is say this is x. Wait, let's think of a function. So we have a function, and suppose at this point it's just not even defined. I don't care. I don't care about the value at this point. But we want to say the limit of the function at this point is, let's draw the y-axis. Let's draw the x-axis. This is L. So the point is, no matter how small an interval you draw around L, say an interval of like radius epsilon, you will find a corresponding interval around here. This is A. You'll find a corresponding interval around A, and in this interval, the function will stay inside the epsilon interval. Like if I Three Blue and Brown Lake has beautiful animations for this, which you can watch that make it very clear what's going on. But so yeah, around the output, you draw a small interval, and you will find the corresponding small interval around the input, and that's the everything inside this input, like the interval around the input, will map to this interval around the output, around the limit, not the output. But does that make intuitive sense?
Can you say that again?
So like you have this is the limit. This is the thing we like are saying is the limit of the function at a, L, right?
Yeah.
So we want to say that this function gets like around a, this function gets very close to L. That's what we want to say. So the way we say it is take like some radius, call it epsilon, around L, and we want to say the function gets like epsilon close to L around A. So we say like for any radius around L, epsilon radius, there is some radius around A where such that you can draw an interval so that this interval maps entirely to this interval.
Makes sense. Okay. Yes.
Okay, thank you. So the way we'll say it is, yeah. So we say limit x goes to a, f of x is L. If for all epsilon, oh, what is that symbol? If for all epsilon greater than 0, once again, in principle, you will only ever pick small epsilon and smaller epsilon, but it is true for all epsilon. For all epsilon greater than 0, so we want to pick a radius around A. So let's call that radius delta. There exists a delta greater than 0, and well, no one writes it that way, but delta depends on epsilon. So I'm just putting it in the subscript to remind you of that. There exists some delta greater than 0 such that if x minus a is less than delta, so if the input of the function is like within this interval, then the output of the function is within, what the hell are my letters looking at today? Then the output of the function is within epsilon. There is just one caveat here, but I'll mention that. But other than that, is the definition clear? I'll just mention one small.
Yeah.
Yeah. Does anyone have any like doubts on what the definition is saying?
Here we are not considering x being equal to a,
Yeah.
right?
Yeah. So like that's the caveat. So like x and equal a. The point is like we say a function approaches a limit at a point, even if at that point the function is doing some random nonsense. Like we say a function that's 0 everywhere, but at 0 it's 1. We still say its limit as 0 is 0. We don't care about the behavior at a. So we add this additional point x and equal a. But that's a small issue. Yeah. If anyone has any doubts, then does anyone have any doubts about motivation or even the like rigorous lines I have written?
I don't think so, no.
No. Okay, good. Very good. And like for continuity, it's very obvious. A function is continuous at a if limit x goes to a of f of x is just the value at that point. Or alternatively, you can take like this previous definition and just remove the x and equal a caveat. And that becomes the definition of being continuous at a. Okay. Okay. Everyone understands what continuity is?
Yeah.
Okay, very good. So now we are ready to tackle. Well, we are not close to ready, but we will try to tackle this problem. So everyone who understands, you can start trying this problem. I will explain for like someone in
Can I give out an idea or not?
Can you DM it to me? I'll ask you just, I want to explain continuity again for some people.
Okay.
Yeah. How do you define continuity? Yeah. Kushagra, do you understand how I define limit of a function at a point?
Yeah, that I understood. What about the continuity part?
Yeah. Okay. So like the idea is we say like look at this function. So and like at a there is a hole and the function actually like maps to 0 or something, right? This is not continuous. Like there's a hole in the graph. So but the point is the limit of this function at a is still L. The limit exists, but it's not equal to the value. So that's all. Continuity means that the limit, okay, I should also add this limit exists because sometimes the limit does not exist. So the definition of continuity is this limit exists, and is equal to the value at that point.
It
For
mean by a limit not existing.
like the function, there is no such else such that this holds.
Okay, okay.
Right? Like if a function is like this, then there is no limit here.
Yeah, got it.
Hmm. Keshav, you need more rigor than that. I'm not sure. That doesn't work exactly. I'm not sure what you mean there. Anyway, so the other way you can think about this as we just for limits we didn't care about the behavior at the point. For continuity we do. So you remove x unequal a. That was to a fact or what? Yeah, this is what do you mean? Like this is just like how we define continuity. Like it agrees with your intuitive idea of what being continuous means. Yeah. Now we'll be trying to see what the set of continuity of a function can look like, which will be hard. This will be quite okay. The answer is no, wait. Keshav, I'm not. You need to make it more rigorous. I don't understand what you mean there. Anyway, so before we like jump to seeing if Q is a possible set of continuity or not, or in fact if okay, let's just start. So okay, can can CF equal R? Can a function be continuous at all real numbers?
Yeah, right. Right.
Yeah, obviously, yes. Just take like any polynomial function or like just any constant function, x equals c, x equals 0, whatever. Yeah. Can the function be continuous at all of R, but not at 0?
Yes, 1 upon x.
Okay, 1 upon x is not a function R to R.
The absolute value function never.
What?
The absolute value function.
The absolute value function is continuous.
At 0, how is it continuous at 0?
Okay. Pick any small interval around 0. Then you have like a small interval around zeros that like maps to this small interval.
Okay, yep, yep.
It's not differentiable, what is what you're thinking about.
Yeah.
A well-defined slope, but it is continuous.
This is okay.
And the issue with 1 by x is it's not a function from R to R, it's undefined at 0.
Wait, how is it continuous for mod x? I
Uh,
didn't.
okay, let's try to see. So the way we define continuity is at 0, like at 0, the function maps to 0. So you want to say that the limit at 0 should also be 0 if it's continuous. So like, let's see, right? No matter what interval we pick around 0, we can pick like actually exactly the same interval for the input. And that will map entirely to this, right? Like formally, for any epsilon greater than 0, for any epsilon 0, let delta epsilon be epsilon. If so what we want, if the input, we want to prove that if the input is within delta epsilon of 0,
Can you
then
explain what is delta again?
like we want, that's the interval we are picking around the input. We want to show it exists.
Okay.
Like, so to prove existence, I'm just giving you an example that this delta works. Seeing? Works. So, so, so what we if x minus 0 is less than delta epsilon, then we want fx minus L to be less than epsilon. And like we are trying to prove the limit is 0, so I'll put 0 here. And fx, well, it's just mod x. Right, so we get mod x minus 0. Well, that's just mod x, which we already know is less than delta epsilon equal to epsilon. The point is, as you go close to 0, this function also goes close to 0. The issue, like, it goes to 0 in like different ways. That's why it's not differentiable. Like, the slope won't be well defined. But as you go close to 0, the function goes close to 0, which is what it means to be continuous.
So what are the conditions for differentiability?
Oh, yeah. Okay, but I mean, I can write down the definition, but it's beyond the scope of this class. There will probably be a proper analysis class, hopefully, where all of this is done much more slowly. I just want to like build to a big theorem as a Diwali gift. Yeah, but I'll tell you. So like, for continuity, what you'll do, differentiability, what you'll do is you like take the slope of any, like, if you have a function, so take a point and take another point, and you consider this line. So the slope of this, like this point is x, this is like x plus h. So the slope of this line is fx plus h minus fx by x plus h, like rise over n, x plus h minus x. And like just write that like this. This is the slope of the line, and we want to say, as you move this point closer and closer to x, this slope approaches a limit. So we say limit. So
Basically,
if
it should
this
exist.
limit exists, it's differentiable.
Yeah.
By the way, the only constraint is that f must be from R to R, right?
Yeah, f must be from R to R. It can be as
Okay,
weird as
so yeah, okay. So for x not equal to 0, define f of x to be sine x upon x. And at x equal to 0, define it to be 0. Then it becomes like
it's,
not continuous at 0, right?
for x n equals 0.
Make it sine x upon x.
Okay.
And then at x equal to 0, just make it 0.
Okay. Amazing. This works. However, here, like, this also works. You don't have to.
Well, okay.
You don't have to try that hard. So, like, at 0, you call the function to be 0. Everywhere else, you say the function is 1. And it's continuous everywhere but at 0. What about DDIT? What are you doing? Guys, no. You're not doing the DDIT. If DDIT happens, Arnav has to take it. Come on. Anyway, everyone understands why this function is continuous at non-zero, but not continuous at 0.
Yeah.
Okay. So similarly, you can also see that CF can also be R minus any finite set, right? Because just like make it 0 everywhere, but remove the finitely many points. Okay, Shagra, wait, I'll come back to. Does anyone have any? Okay. Do we just go to Q? Because there's really like no way I can build up to it. Okay, I'll give everyone like 5 minutes to try Q while I answer some doubts about everything we have covered till now. After that, I'll start hearing ideas for Q. I think a few people have ideas. Wait, what? Kushagra, what are you saying? Leave. What? No, sure. Okay, we do it. Okay, Keshav, you had some idea for Q, right?
Yeah. So basically, what you do is,
Hmm.
suppose it's like for the sake of contradiction, suppose it's not continuous at some irrational number g.
Okay, so suppose we have FR2R that satisfies this. Yeah.
Wait, but actually, now that I think about it, can't we just define it to be piecewise? Like suppose it's okay, make it 1 at every point, but make it like 0 at root 3 or something. Wait, what's the question again? Do we have to
Question
show
is it
we have
possible
to
for there to be a function R2R that is continuous at all rational numbers and at only rational numbers?
Okay, so it can't be continuous at irrational numbers, right?
It can't be continuous at
Yeah,
the right
yeah,
place.
yeah. Okay, okay. So basically, what you do is suppose you have like some irrational number where it's not. So I'm claiming the answer to be no.
Okay, there's no such function. Okay, sure.
Yeah. So what I'm trying is that take some irrational number j, for which the function is not continuous.
Okay.
Then what you can do is because at rational points around j,
Hmm.
the function has to be like it has to approach j, right?
Yes.
And then because you
No.
can
The mm,
because the irrationals are infinite, that just doesn't work out. I mean, I
no,
don't know
no,
how to put
no,
that
no, no,
precisely,
no, no.
but
There is J here. There is some rational P close to J. Around P, the function has to approach P, and P is not J. For example, your argument seems to imply that the function should be like continuous everywhere if a function is continuous at Q, right?
yeah, like continuity at q extends to r.
Yes, but that's demonstrably false. You can have a function that's discontinuous at a single point.
Yeah,
I don't think this is true.
What do you mean?
I don't,
What's like?
I don't think that you can have a function PFS.
It's like find construction or prove it can't exist.
How can you prove it that it can't exist? Right?
How do you prove it?
How do you even try to go that way?
Yeah, so one idea, like someone told me, like to try for some like whenever you want to prove that some crazy looking mathematical object can't exist, you try to construct it and see what goes wrong. I don't know why I'm writing 5 anymore. So can you tr try to construct a function that's continuous at only q and see what kind of issues are you are having?
I have a question.
Hmm.
What's the problem with defining a function like fx equal to 1 if x is rational and
Hmm.
0 otherwise?
Okay. Fx equal x and q, not in q. Well, where is this function continuous?
Like it's continuous at the rationals, right? Because
Why?
like you don't have irrationals that are very, very, very close to each other, right? So you
There's
have
not. No. Look at 0. Take 1. So like what do we want? For any epsilon, so like I'll just pick as a counter example, I'll pick epsilon equal half. So we want there should be some interval around 0 where this function is within half of 1, right?
yeah,
But any interval around 0 will contain an irrational number. And if it's irrational, it maps to 0, and 0 is not within half of 1.
right, yeah, makes sense.
Yeah, this is a classic example of a function that's discontinuous everywhere. Hmm. So by the way, like as a reminder, this class I'm doing just because, well, there is Diwali tomorrow, so I expect low attendance. So this is completely irrelevant to anything else we'll be doing. Like my next higher math class will, actually be reasonable. I will not come and give you a very hard problem. I'll probably do like basics of rings.
So can you argue that something like rational is just um, it's- they are they can't be continuous. Rational itself is not a continuous set.
Hmm.
You not uh,
Just because rationals are not a continuous set, that doesn't mean it can't be, well, like once again, like, okay, will you call this set, like all real numbers except zero, is this set a continuous set?
yeah, I would call this a continuous.
Okay, then you need to define for me what a continuous set is.
Okay. I mean, a continuous set in the sense that you cannot fill a line with rationals, right? So it's like you will always have these gaps between the rationals with irrational numbers, which are not supposed to be to a similar
Wait,
level.
okay, let's do a different thing. Then wait, let's do the can CF be only zero?
CF can't be any finite set, right?
It can. In fact, CF can be any finite set. Okay, can someone give me an example of CF being zero? Fx equals zero is continuous everywhere.
I can use sine theta again if that works.
Go on.
So fx equal to x squared sine 1 upon x for
This is
all
continu
x not equal to 0.
this is continuous everywhere except zero.
Oh my god.
Already. This is already continuous a lot of other places. No, I don't think it's possible. Ooh, you're going to be surprised. Okay, I'll give you a hint. Think about this function. So the idea is very similar to what we did above. You basically take two functions and splice them together by using rationals and irrationals. So you take a function that maps every rational number to itself and every irrational number to zero. So like if you look at this function, it will look like two lines. But the thing is, both the lines have holes. This function, like this line only exists at the rational numbers and the x-axis only exists at the irrational numbers. So at any point, the function isn't continuous because like go to like some rational number, say like 5. Then like the rational numbers around 5, they map to things close to 5. But the irrational numbers around 5, and no matter how close you go, there will be irrational numbers around 5. They'll map to 0. And like this is like a very large distance. So like pick epsilon equal to 2.5 or whatever, and that will fail. Similarly, the irrational numbers face the same problem. For any irrational number, because all the irrational numbers are going to 0, right? That's why like this will also exist. Neither of these are lines. They have a lot of holes. The x-axis has holes at all rational numbers. The x equal y line has holes at all the irrational numbers. But they look like lines because I can't draw that many holes. Yeah. Similarly, like every rational number is a problem because no matter around any irrational number, you will always find some rational number, and that rational number will map to something that's like very far away. So this is not continuous. The one exception, 0. Around 0, no matter if you have an irrational number or a rational number, they both map close to 0. Hence, it will be continuous there. Does everyone understand how this function is continuous at 0 and only 0?
Okay. So any finite.
Any finite set? Yes, yes. You can get any finite set by, well, like, so suppose you want it continuous at these points. So what you do is you make it 0 at all rationals, and at irrationals you make like a something like this. Like just splice together 3 lines. Or make like a polynomial with these 3 as roots, if that works better.
Okay, makes sense.
In fact, you can also have CF equal N. Can someone give me a construction? You don't have to like describe it with like equations. You can just explain to me what I should draw. Like a function continuous at all what am I doing with n, bro? Z. A function continuous at all integers and only at the integers. Wait, that's discontinuous at the integers, bro. That's the wrong way around. Yeah, but that's an example for sine pi x. Okay, no, okay, I see what you're trying to do. So what you're saying is like take the sine function and like let a function be sine for all rationals and for irrationals make them 0. Right. Once again, like the trick is you splice together two functions and the function is continuous only when those like two splices intersect. Does everyone understand this? Like take, well, instead of sine, you can take like a much simpler thing. Just like take a alternating. Oh wow, this is a horrible number line. Take like in this alternating function. Let this be the function for all irrationals and like an alternating function with like period 1. Can you explain construction part again? Kushagar, I'll explain like something after class, but I think I'll continue for now. Yeah. So like up and down, up and down. Yeah, I'll like explain later if you want. Yeah. It goes up and down and for rationals and for irrationals it's 0. Once again, everyone sees why this will be continuous only at the integers, right?
Yeah.
Yeah. Good, good. So as you can see, there's like very weird things going on. What is so special about Q? Like Z works, R works, and like somewhere between them, well, I'll tell you the answer. It's not possible for CF equal Q. CF can never be Q. But just Q somehow in the middle it breaks.
Wait, can you explain again why the integer thing works?
Sure. So it is about the measure. I'm not introducing measures. Do not worry. It has something to do with Q being dense in R. Yes, good intuition. So what? Yeah, so the function, no, I won't write this function down. So the point is, like I take this alternating line function, whatever it is, and I say if f, like let fx be the alternating line function, and I define gx to be f of x for x in q and 0 for x not in q. Right. So for any rational number maps to 0, but like take any interval around it, the rationals are mapping to other things. So it won't be continuous. Similarly, take any rational number. The irrationals in any interval around it are mapping to 0. So that doesn't work. The only way it works if you take this, because even though the rationals around it are mapping to 0, the irrationals around it are also mapping. So no, I said the other way. The irrationals around it just map to 0, and the rationals around it map close to 0. So it's continuous. I just gave an example for the thing. What?
Wait, I still don't get it. What?
Oh, wait, let me make it more clear. Let's use sine. I think everyone should be. I was avoiding sine, but bare category measure. You're not wrong, but like I am not introducing insane notation to solve this problem. I'll solve this without it. Oh, what? Sorry. Q and not in Q. Yeah, sine pi x for x in Q and 0 for x not in Q. So what will this function look like? So all rational, first of all, sine pi x is 0 at all integers, right? So the sine pi x will just look like this alternating curve that hits 0 at all integers. And like this curve has holes at all the irrational numbers. And okay, this is meant to be the x-axis. What the hell am I drawing? Anyway, so suppose you take. Oh, that doesn't even bother. He just scribbles over it. Suppose you take some irrational number. So what does the irrational number map to? Wait, Akshar. Irrational number maps to 0. Right. So now pick some like small epsilon, like I don't know. I mean, this is like okay. Pick some small epsilon, just like this stretch won't always work. Just the point is pick some absurdly small epsilon. The point is it should be smaller than this length. Like pick epsilon to be the half of this length. Okay.
Yeah.
So now any interval you draw around this input, this interval will contain a rational number. Like every interval of the real numbers contains some rational number, right?
Yeah, it does.
That rational number will map to like this point on the graph,
Okay.
which is farther than epsilon.
Yeah.
Similarly, if you start with some point on the graph, the interval around it will contain some irrational number, which will map to like some point that's farther than whatever epsilon you pick.
Yes.
Only difference, the only time it won't happen is when these two graphs intersect. Because then the like this height is just 0. So it doesn't matter.
Yeah, that makes sense. Yes.
Okay. Yeah. That's good. Oh yeah, I do have an eraser tool in Miro, don't I? Maybe I should use it. Anyway. Okay, before I go further, okay, there is no, you don't need that theorem. I was thinking about mentioning a theorem you might need, but no. I'll prove it in a way that you don't need anything except the definition of continuity. Okay. So this is by no means an easy problem. So now let's try to do something. So what the idea, wait, who was it? The idea Keshav has was, well, sort of the correct thing. For any irrational number, there will be a lot of rationals close to it. So we want to prove the fact the function is getting close to the rationals also implies the function is getting close to this irrational number. Right. This is basically the idea Keshav was trying to do.
Yeah.
Everyone's, yeah. The issue with this idea is like, we know for a fact this won't work because we know like, if instead of q, we had like r minus square root 2, we know this is possible. Okay. So the idea is, take some irrational number, say root 2. There are lots of rational numbers close to root 2, right? And we know the function is continuous at all these points. Right. So the function, like, so we have root 2. we have some p by q, and p by q is very close to root 2. And we know the function around p by q is very close to p by q because the function is continuous at p by q. Right. So we have root 2. We have p by q close to root 2. And close to p by q, the function is close to p by q. And p by q itself is close to root 2. So we should try to say that that means the function is also close to root 2. Right. And that will give us a contradiction because then the function is continuous at root 2.
Wait, f of p by q is root 2, right?
No. F of p by q can be anything. We don't know what the function is. We are trying to show no function exists. So for the sake of contradiction, assume some function exists. For the sake of contradiction, f R2R such that CF equal Q. Suppose it exists. It's continuous only at rational numbers. For a contradiction, we will show it's also continuous at some irrational number. That's what the contradiction will be. Right, Anirudh?
Okay.
So like the idea that we thought that Keshav had was pick some irrational number. Say you pick root 2, right?
Okay.
So we want to say that this function is like around root 2, it takes close values, values that are close to each other, right?
Yes, for
That's what it,
rational.
that's what it, no, just like if we want it to be continuous at root 2, we want to say that for like some interval around root 2, the function is
Okay.
very close to itself, right?
Yes.
But we don't know anything about root 2, but we know take a rational close enough to root 2. Around that rational, the function is close to itself because it's continuous at rational numbers, right?
Yeah.
So the idea was you take root 2. If you pick a rational that's very close, somehow this interval will also encompass root 2. That's our hope.
Okay. Yeah, I got it.
Yeah. But this hope is, well, flawed because it doesn't have to be, because it's absolutely possible that a function is continuous everywhere but root 2. Right. Given any particular irrational, we can't prove the function is continuous there because it's absolutely possible it's discontinuous there. Right. We just demonstrated examples of functions that are discontinuous at exactly one point. Right. Hmm. So the key observation you need to have is you can't start with an irrational number and start picking rationals close to it. That will just fail because this function can be discontinuous at this irrational number. What you need to do is pick rational numbers and take irrationals close to them. Hmm. Everyone sees what I'm sort of trying to do?
Wait, okay, so is this what you're doing? So you make the rationals sort of, so suppose you have two rationals that are very close to each other. You're
Hmm.
trying to pick an irrational between them.
Not exactly. Because once again, it can be possible that like there are very small intervals around the rational numbers. By well order, no, well ordering will not come in. Don't stop. Yeah, anyway, okay, sure, yes. The thing is, once again, so what I'm like intuitively hinting at here is let's be a little bit more formal. Suppose you have a rational p by q, then like pick say epsilon equal half, then there exists like a delta half interval around it, and similarly we have like p prime by q prime, it has like a like delta prime half interval around it, but these intervals can be very small. It's entirely possible they don't intersect.
Right. Okay, makes sense.
If you ever take two numbers, it's entirely possible their intervals don't intersect. If you take two random numbers, the idea is we will try to rig our choices to ensure their intervals intersect.
Right.
How can you rig your choice?
We can choose two rationals that are just ridiculously close to each other.
No matter how ridiculously close you choose, if you make the choice already, then I'll just tell you, oh, it just happens that their delta halves intervals are very small. Like their radius is like precisely half the like not half, one third the distance between them. Unfortunate. What will you do? See, the first observation was you have to like, instead of picking irrationals, you should pick rationals. There's a second like key idea you need. So the first idea, pick X in Q, not. And like the motivation behind this idea is we know at any particular irrational, it can be discontinuous. So picking any particular irrational will never work. So we should pick a rational. Okay, this is idea one. Now I'll give you, before I start, I'll try give you some time to think of the idea. So
So basically, you want to have two rationals such that their deltas are intersecting so that they can't, the numbers in that intersecting interval can't make a choice between the two rationals.
wait, yeah, not exactly. Wait. So okay, so what I want to do is this. Say if you have say epsilon equal 1 by 4, right? And say there's some delta 1 by 4 interval. That means that like say we have a, so a minus delta 1 by 4, a plus delta 1 by 4. I should have said this earlier, sorry. Yeah. So like take this interval. In this entire interval, like the epsilon delta definition literally means like, so somewhere here is f of a. The epsilon delta interval literally says that any any x value that you pick in this interval, it will have a y value that's within 1/4 of f of a, right? That's what epsilon delta says.
Yeah, makes
Like
sense.
at worst, it's 1/4 below f of a. Actually, since the inequality is like not strict, it can't be exactly one, but no one cares. At worst, it's exactly it's 1/4 below, and at like in the other direction, at best, it's 1/4 above, right?
Yes.
So any 2 points in the interval, they are at most a distance of half apart.
Oh, yes.
So suppose you have an irrational number b here, right? Then like take any smaller interval that's contained inside the bigger interval around b. In this interval, every number is like at most half apart, right?
Oh, wow.
Every That means this interval will be a valid delta half interval.
Yeah.
It's not a valid delta 1/4 interval anymore, but it's at least a valid delta half interval.
Yes.
So for any irrational, if you want to find an epsilon interval, then it's sufficient to find a rational close to it, such that it's that rational's epsilon by 2 interval contains this irrational.
Okay, I'm lost. What?
Okay, let's go back. So let's go back. So what we had? We had a rational number A. We had a delta 1/4 interval around it, right?
Yeah, I agree with this.
In this interval, every f value is within half of each other, right? Because they're at max half below f of a, 1/4 below f of a, and like at worst 1/4 above f of a. So they're all within a half interval.
Yeah, makes sense.
So like pick any irrational number b here, right? F of b. So suppose this is f of b, right?
Yeah,
All values of f in this interval are within half of f of b.
they are.
So what we are basically doing is triangle inequality, right? F of b minus f of a less than 1/4, f of a minus f of c less than 1/4, so f of b minus f of c less than half,
Yeah, that makes sense.
right? So in fact, you can like say that there is like some interval around b where everything is within half of b. F of b, right?
Yeah,
So like if suppose you were trying to prove continuity at b,
yeah.
if someone gave you epsilon equal half, then you already have a delta half interval, right? Just this interval.
Yes, you do.
So the idea we had to begin with was pick an irrational number, b.
Yeah.
Suppose we want to prove continuity, that means we want to prove something for all epsilon, right?
Yes.
Pick any particular epsilon, say epsilon equal like, I don't know, 1 by 54. Okay.
Okay.
If we can find a rational number here, a, such that for like rational number we know are continuous. That we have assumed for the sake of contradiction.
Yeah. Yeah.
So for no 1 by 27, yeah. So take for a, take the 1 by 27 epsilon equal 1 by 27. We will have some delta interval.
Yeah. You will.
Sorry. No, I should go the other way. Epsilon equal 1 by 108. Okay.
Okay.
So suppose by some miracle that delta interval happens to contain B.
Okay.
Then we know like everything is within 1 by 108 of f of a. So everything is within 1 by 54 of each other. Right? At most 1 by 08, 1 by 108 above, at worst 1 by 108 below.
Yes. Yes. Yes.
So that means there is an interval around B where everything is in 1 by 54 of each other.
Oh yeah. Yeah.
Yes. So the idea is for any A, any, let's call it X. Yeah, for any X not in Q, if we want to find like given some epsilon, if we want to find delta epsilon, we can instead find a rational close to X, call it A. And if that rational's epsilon half interval contains X, then we will have an like if delta epsilon by half, consider this interval. If this interval for A contains X, then we will get a delta epsilon interval for X.
Basically, this will show that you will have continuity at X also.
Yes, but the point is you need to do it for all epsilon.
Yeah. Yeah. For all.
For all
Yeah.
epsilon. For every, or not all epsilon, for every small enough epsilon. Because if you do it for some epsilon, like that also works for like epsilon plus 5.
Yeah. Yeah. That I get.
So for small enough epsilon, you need to be able to find an epsilon by half interval that contains X.
Okay.
Okay? Makes sense?
I think it makes sense.
So like this is so like the idea that Kushagra had, if like no sorry, not Kushagra, Keshav had, in more rigorous footing is like that. Like for any rational, we want to find close enough rationals. But once again, that didn't that we know won't work. So now instead we pick a rational. We pick a rational X. Okay? So take its epsilon equal 1 interval. Okay? No, wait. Let me wait. Does it have anyone had some ideas about like the second issue we had?
Yes. So, okay. So, as I understand it, the second issue was that if I fix the rationals, then you can always choose a small enough epsilon, right?
Yes. Delta, small enough delta. So
Yeah,
shall I do it?
yeah, small enough delta. Yeah. So, what if we were to uh, rig the rationals by using epsilon and delta?
Okay, go on.
So, okay, I don't know how to like rigorously do this, but what I'm saying is, suppose we want to, suppose we have a rational, right?
Yeah, yeah,
Then instead of fixing a second rational and looking at like the irrations between those two,
yeah. It's irrational.
yeah, I don't know. So okay, suppose you have,
Suppose you start at 0.
yeah,
Does not
suppose you
matter.
start at zero. Yeah.
Yeah.
So we're trying to build an interval around zero that contains irrationals, right?
We are trying to build an interval around 0 that contains irrationals. Okay, yeah.
Wait, I don't know what I'm doing.
Wait. Let me help people out here. Okay, let's go ahead. So okay, so start with 0. Start at 0. Take 0 in Q. So pick a okay. Ahan has some idea. Pick a rational. There's always a delta interval for every epsilon. This delta interval contains an irrational. There is an irrational. Okay, yes. So what you are saying, but what we actually want is for a particular irrational, there should be every epsilon. What you are getting is for every epsilon, there is a, sorry, for every irrational x. No. For some particular irrational x, there should be every epsilon, like every epsilon should have a corresponding interval. Ahan, what you are doing is for any particular epsilon, you are getting an irrational that has that corresponding interval. But we want an irrational to have all epsilon, not all epsilon to have different irrationals. Oh, wait, my camera has been off this whole time. Why did you not tell me? Guys, viewer attention should be up now.
Wait, I can already feel myself solving the problem with the bunches.
Yes, yes, this is the last motivation we need. Okay, yes, Ahan, he understands. Thank you. Okay. Yes, yes. Okay, so start I'll start saying stuff, and if you at any point you see how it's going, feel free to stop me and start yapping instead of me. Okay. But Ahan, what you're doing is also like sort of relevant. So take 0. That's a let's take a empty place, please. So take 0. That's a rational number. So for epsilon equal 1, we will have some delta 1 interval around 0. Okay, this is a delta 1 interval. So what we wanted was for some irrational, like some irrational x, there's an interval corresponding to every epsilon. In fact, I like relax this condition. The bunny cap would have the right Fourier analysis. Oh my god. Like we only want small enough epsilon, right? So what I'll do is if I can say for some x, an interval corresponding to epsilon equal half exists, 1/4 exists, 1/6 exists, 1/8 exists, and so on, then I am done. Right? Instead of finding intervals for all epsilon, I'll just find intervals for these particular epsilon.
Yeah,
This
uh,
that would be sufficient because we are getting small enough epsilon. Yes?
yeah, I think correct.
Yeah.
Yeah. Okay. So here's the thing. So for yeah. You know what? Let's add 2 more numbers. 2, 1, half, whatever. Does not matter. Yeah. So for 0, take epsilon equal 1, and there's a delta 1 interval around it. For every irrational in this delta 1 interval, we have already found like for any irrational here, like any irrational A, we know an interval for 2 exists, right? Because that's what we just discussed above. For any of these irrational, an interval will exist for epsilon equal 2 because they are contained in an interval for epsilon equal 1.
Yeah, that makes sense.
That's what we just did. Like for every rational inside this interval, a double interval, like they have a double, like an interval for double that epsilon. Okay. Yeah, I should not. These are the wrong ones I wrote. Yeah, sorry. For x, we'll find 2 by 1, 2 by 2, 2 by 3, 2 by 4. Like, we'll find these intervals. But it doesn't matter. I'm just saying it already. Ideally, you'll like do the whole proof and see what epsilon intervals we have come up with. Anyway, for every rational inside, we already have an epsilon equal to interval. Okay. Now, here's the idea. Instead of starting by picking 2 rationals, you defer the choice of the second rational till after you have picked the second rational. Right. Pick the second rational number already inside this interval. Because now the intersection is forced.
Yeah, that's yeah.
Yes. So now let's go down here and increase the size. Wait. So suppose this is very big interval because I want to, for demonstration purposes, this is the delta 1 interval. Pick another rational. It can be any rational. There will be some rational here, obviously. Pick some rational here, A and Q. For that rational, take the epsilon equal half. There will be a corresponding there will be a corresponding delta half interval. Right? And for every
Yeah.
irrational inside this delta half interval, we already have a delta 1 interval because they lie in a half interval.
Yeah.
Right? So, and since this interval is a subset of the previous interval, every irrational inside this interval has both a delta half interval and a delta 1, no, sorry, has both a delta 2 interval and a delta 2 by 2 interval already, 2 by 1 and 2 by 2.
Yes.
Can anyone see where this is going?
Okay, so my hunch is that you keep on constructing these deltas and then you just finish by what we discussed above.
Yes. So yes, basically, but there is one subtlety that I'll once again address. Once again, so now you look inside this smaller interval, this delta half interval. One, you pick another rational number inside, right? You pick the interval around it. This time you choose epsilon equal 1 by 3. Now all irrationals here, they satisfy like both 2 by 1, 2 by 2, 2 by 3. Once again, you go inside another rational, another interval. All the rationals there will satisfy 2 by 1, 2 by 2, 2 by 3, 2 by 4. You keep doing this, and eventually you will have an irrational number that satisfies all those epsilon, all of them. Except, well, there are two issues. Uh, so the issue number one, how do we know that? Okay, let's explain the issue. So you'll look at this proof. Okay, who here thinks the proof is complete? Who here does not see an issue? I might be lying
No,
to
I
you.
don't. No, I don't think it's. There might be some gaps,
That's not exactly the issue, but yeah,
but
I'll explain. Okay, so the main issue is for like any finite number of steps we do, we will find an irrational number, right? We have an open interval, we have an open interval inside, we have an open interval inside, we have another open interval inside. We will find something inside. But at the end, we want to take the intersection of an infinite number of open intervals. The infinite number part is a bit sus, right? Like finite number, everyone's happy, but then infinite number of intervals, yeah, like you can't you can prove everything for all natural numbers. That doesn't prove it for infinity. This is not induction, right? That's one issue. So like also like someone hit yeah, that is one issue. And like how do I do this? Yeah, okay. So that's the theorem I wanted to mention earlier. By nested interval, you can almost finish, but even nested interval leaves some issues. So like nested interval theorem, I want to mention it. I'll try to work around it. Anyway. The other thing you might think is like, wait, why are we even picking different rational numbers? Right. So take 0, you have some interval around it. Pick 0 again, you have a smaller interval around it. Pick 0 again, you have a smaller interval around it. What's the issue in this? Why do we want to even pick different rationals? Because no fixed irrational. Exactly. That's the point I had. Yeah. There is no fixed irrational inside this. Like any irrational, like there is some irrational here, but like eventually this irrational will stop lying there. In fact, any irrational will eventually stop lying there, and the only thing you'll be left with is 0. So you're left with something, but it's not irrational. So like, for those of you who have heard of nested interval theorem before, nested interval theorem will tell you that even with an infinite number of intervals, we can find at least one point inside. But nested interval isn't enough to conclude that one point is rational. Okay. Yeah. Well, how do we fix this?
so
Yeah,
if in
nested
the
interval,
end,
this is
if
the
we
point.
want, yeah, so if in the end we want a irrational number,
Hmm.
why aren't we building the intervals around the irrational? But then doesn't that just loop back to the original issue?
No. Once again, you cannot build intervals around any particular irrational, right? Because for any rational, you don't know if it will contain a specific irrational. Like the whole point is we don't know which irrational we will end up with. We just know that we should end up with some irrational. So here is uh here is sort of the, well, how do I consume dihydro? Okay. I don't know why people in chat keep asking me to drink water, but I'll oblige. Okay. So the idea is we still have a lot of freedom left in this problem. Okay. We have a lot of freedom in how we are picking the intervals, right? Because there are infinite rationals inside, right?
Yeah.
We can exploit this freedom to ensure there is like to assume that there will be no rational number left. How do I do this? Let me. Okay, I'll. Okay.
You have the freedom to choose any rational with which
Mhm.
you want to consider the delta intervals, right?
Yeah, yeah.
Eventually, there should be one rational such that if you
Not one. There'll be lots of choices, but you're saying there should be some.
there
Hmm.
should be some, at least one,
Hmm.
that if you close on its delta intervals will eventually end up with an irrational.
Hmm.
Right?
When a proof is left and exercise to heal never. Thank you. Okay. I wonder if I want to like just cite like if I cite nested interval theorem, then the next steps become like much easier. But I don't want to like. Okay, here's the thing. How about this? I'll do a proof by just citing nested interval theorem, which you can prove by like stuff. But then I like after that, if you're not happy with that, I'll also like explain how you can work around that. Or I'll just prove nested interval. That will actually be the better idea. We'll see. Anyway, so what nested interval theorem states is you have if you have a list of intervals, I1, I2, so on, such that like they are subsets of the previous one, then there exists X such that X in I for all I. So like they have a non-empty intersection. The caveat is these are all closed intervals.
Sorry to ask, what's the difference between a closed and open interval?
Closed means it contains it. So like the open interval 0, 1 means all numbers between 0 and 1, not including 0 and 1. Closed means like you also include 0 and 1.
Okay, okay.
Uh, so whenever I defined continuity, I used these inequalities instead of these. So all our intervals are open. Thankfully, like, okay, can anyone see why this closed interval, open interval issue is like not really an issue? Hmm. There's no
I
just
mean,
point to
the
like,
subsets, right?
yeah, exactly, exactly. So like for any open interval you have, you can just pick like a smaller closed interval. There's no issue, right? Also, you can also show that the definition for continuity, if you replace less than by less than equal to, it is equivalent. Either one works. Like no one has, does anyone have any issues with me replacing every open interval everywhere with closed intervals? I
No.
don't. Yeah. So for now, I will assume this theorem. I'll assume this theorem and prove that we have something. Once again, okay, this theorem also isn't enough. So what we are doing now, we are picking like closed intervals inside closed intervals inside closed intervals. And the theorem tells us that eventually we will end up with at least one point, which is great. Except that point can be rational. Like that's what happens if we just keep picking the same rational again and again. We do end up with a point. It's just a rational number. And nested interval unfortunately says that there is at least one point. It doesn't say anything about multiple points because it's false for multiple points.
Slight question.
Hmm.
So, what if we iterate this theorem
Hmm.
many times?
What do you mean?
So, suppose you have the interval 0 to 1, right?
Hmm. Hmm.
So, add a small enough epsilon
Hmm.
such that the last number that you get shifts by a little bit.
Okay.
And because like the numbers are distinct and you can take smaller and smaller epsilon, would that guarantee getting an irrational at some point?
Okay. You have the correct intuition, I think. I think I see what you're saying, but like I'll say the same things more rigorously. Okay.
Yeah.
Okay. So what we want to so what we'll do is okay. We don't know how to guarantee it won't be rational. Okay, can you at least guarantee that the number we pick won't be a rational with like x equal p by q with say q less than equal to 5? Can you guarantee that if it's rational, its denominator is more than 5? Like we will end up at some x, and that x might be rational. We are trying to ensure it's not. Can you at least guarantee that if it's rational, its denominator is more than 5? No, I'm asking, can you? Like we still have the freedom of how to pick the intervals left, right? Like where to center the intervals around. Can you use that freedom to guarantee that the denominator will be more than 5?
Less than 5 or more than 5? You have
More
written
than
less
5.
than 5.
Like, sorry. Like, okay, so we know we end up at an x. Guarantee that x not in, in lowest form, guarantee that either x is irrational, in which case we are very happy, or x and q, x unequal, yeah. So x cannot be expressed as a fraction with denominator less than 5, and like q greater than 0, p comma q and z, p comma q and z, the standard business. So guarantee that if you end up with a rational, it won't be a rational with denominator less than 5. How do you do this?
You can explicitly mark
Switching the interval.
But wait, Akshar, first you, then I'll ask Akshar.
the rationals with the denominator less than 5 since rationals are countable, and then
Yeah,
try to like not contain them.
precisely. So like whatever interval we started with, like interval around 0, we have this is our delta 1 interval. Like you mark all the rationals inside that have denominator less than 5, and there are, forget countable, there are finitely many. Right, there will be like a few in, like suppose there's one here, minus one here, then there will be like minus half here, half here. Maybe there's like also 3 by 2, I don't know. But that's like only finitely many, right?
Yeah, and we've got infinite choices to
Yeah.
choose.
So like now go to some rational number that's not any of them. And like there's only finitely many things we have to avoid. So like whatever interval we get, like just pick an interval inside it that's small enough that does not contain any of these finite choices. There's an infinite number of rational numbers inside this interval, and only finite rationals we have to avoid.
Okay. Do you mean to say that the number of rationals inside this interval will be finite?
Infinite. Number of rationals is infinite, but number of rationals with a small denominator is finite. And we just want to, currently we are just trying to avoid small denominators. Right. So like there's a finitely number of things we want to avoid. So forget, like we have a lot of freedom. Even at the second choice, we can guarantee that we don't have a small denominator by just like picking a rational that doesn't have a small denominator and picking a small enough interval around it that doesn't contain anything with a small denominator. Is everyone clear that like, so I1 we are like forced to pick like whatever we get from 0. From I2, we have already guaranteed that there is no number with a small denominator inside. Small
Yeah.
being less than equal to 5, right? But
Because
here's the thing. We have so many choices left. So by I2, we guarantee that if it's rational, Q is greater than 5. With I3, do it again, but this time guarantee that Q is greater than 6. Then pick I4 in such a way that forces Q to be greater than 7. ... And now if we know by nested interval, there will be some number inside all of these. And the fact is, we have guaranteed its denominator is greater than any natural number. But the denominator certainly can't be infinite. That means it can't be rational. The function must, the x that we get must be irrational. QED.
That made sense.
That made sense. Thank you. I don't know if it. Okay. How many people does it make sense to? Assuming nested interval, how many people does this proof make sense to?
Yeah, it makes sense. It's very local in nature.
Yeah. Okay. Makes sense. Very good.
The
Very good.
nested interval shouldn't be that hard to prove, right? It's just
Oh, a nested interval is yeah, I like even like okay, the thing is technically you haven't had an analysis class that formally defines the real numbers.
By
Like
the
with
way,
yeah.
uh, to be fair, can I just use like Venn diagrams to prove nested interval theorem?
No, nested
Like because
interval is also
everything is a
like
subset.
uh nested
Because
interval
everything
is
is a
false for
subset of
open
my stack.
intervals.
Ah, right.
Like here's a counter example. Consider the open interval 0, 1, then 0 half, then 0 1/3, and so on. Their intersection is does not exist.
Yeah, makes sense.
Their intersection is empty. You cannot use that. So for like for general metric, how do you say that? There's how do I prove this? What's the easiest way to I can tell you nested interval? The thing is to prove nested interval, you sort of require like I will have to. I can just tell you a property of the real numbers, but well, to not use G delta, we have few. Yeah. Uh, there's okay. Wait. Let's see. Okay, so here's an idea how you can do this proof like without nested intervals. But like that also like is sort of a scam because I sort of intrinsically assume the real numbers are defined, but I just cover it in like cloaks and daggers. So do I want to scam you? Who here wants to be scammed?
I love to be scammed.
Okay, let's scam you then. Okay, so everyone agrees that if I give you a everyone agrees that if I give you a sequence of like numbers between the integers, natural numbers, no, is zero natural? It depends on who you ask. Integers between 0 and 9, if I give you a sequence of them, then you will have a corresponding real number, right? Every sequence of digits, if you write it out in decimal, corresponds to a real number.
Yeah.
Everyone agrees? Yeah.
yeah.
So like this is sort of the scam. I assume that you already like have defined the reals. But like the decimal notation is easier to digest for everyone, right?
Yeah.
So the way I would like do it is I like we have so much choice left in our intervals. So the first time I pick an interval, uh like I ensure that it like contains okay, first let's see. So suppose the rational we have picked is like 0.25. Okay? Then that means like any interval, we have some interval around this, right? Uh, Suppose like this number here is what? 0.25781 something. And this number here is 0.259 something In particular, you will notice that every number that starts with 0.258 is inside this interval, correct? Because any number that starts with 0.258 must be bigger than this and smaller than this.
Yeah, that makes sense.
So what you do is like, so just here is 0.258 and here is 0.259, right? Pick this interval. Like instead of picking the whole interval, you pick a smaller interval because you can do that. This interval still satisfies all the properties, right?
Yes, makes sense.
And so what we are doing is we are sort of constructing x in a sense. So now we know the first three decimal digits of x. The next interval will give us like a few more decimal digits of x. The interval after that will give us even more decimal digits. And since we have a sequence of decimal digits, we know x exists. We have basically constructed it.
Okay, yeah.
And
That
like you can also like you can convince yourself that like both these finesses, the finesse we did to like prove x exists and the finesse we did to prove it's not rationals, you can convince yourself that you can do these both together. The idea is you first do this, like pick an interval that doesn't contain anything with a small denominator, then make that interval even smaller to rig the decimal digits. Like this is a scam, I admit it, but do you sort of follow this?
Yeah, sure.
Yeah, so like whenever there's an actual real analysis class, I'm sure nested interval will be proven, or at least you will be given the tools to prove nested interval. Like I'll just mention it here. The proof of nested interval relies on something called LUP, least upper bound, no, LUB, least upper bound. So like the reals have least upper bound property, whatever that means, and from that the proof of nested interval is direct. So whenever someone says least upper bound in a class, remember this and come back and prove it in a less scammy way. But this is still a fine proof, I hope. Okay. If does anyone have any doubts till now? Any questions? Everyone understands like at least the key ideas of this proof.
Yeah.
Okay, everyone understand? That's anyone has enough I can ask because I have like I want to like I'll mention some amount about like the general question, how do you classify all of CF? But this was actually like the hard part is done. Every idea we used here will generalize to the general thing. So I'll just mention it and leave it as an exercise. Some more rigorously, the J and B is in fact equal. Well, they're not in fact equal, but like the point is sub A is less than equal to inf B. They might be, if they are unequal, then we have infinite numbers. If they are equal, then we have a single number. But yeah, like whoever understands what sup and inf mean, you can read what the person in chat said. That's the proof of nested interval. Anyway. Anyway. Okay, if no one has any doubts, I'll like now finally mention the general case a bit. So the a set like okay, here's the notation. So this is G and this is that look at this G delta. G delta is a property that subsets of R can have. Not okay, subsets of like general topological no, metric spaces, but for our purposes, subsets of R can have. So some subsets of real numbers, we say they are G delta if they satisfy certain criteria, which I'll mention now. And the like main result is S equals CF is possible if and only if S is G delta. Okay, like I'm abusing notation a lot here, but a set can be a set of continuity if and only if it's a G delta set. That is the result. Okay, so what does G delta mean? So what we did is like we took an interval around 0, and then we took like a smaller interval, then we took like a smaller interval inside. But like another way to sort of write this proof is like take all the intervals at once. I'll explain. So for 0, we will have like some delta 1 interval. For 1, we will have some delta 1 interval. 2, we will have some delta 1 interval. Half, we will have some delta 1 interval. Right. For every single rational, we will have some delta 1 interval. Right.
Yeah.
So consider the union of all those intervals, call them D1, capital D1. Now, any irrational inside capital D1 has like a delta 2 interval, right? So like instead of just looking at 0, you consider all the intervals at once, and any irrational anywhere will have a delta 2 interval.
Yeah.
Right. Similarly, now for 0, there will be like a delta 2 interval. 1, there will be a delta 2 interval. 2, there will be a delta 2 interval, and so on. So consider D2, and every irrational inside will have like that, like a delta 4 interval. Sorry, not delta 2, delta half. And every irrational inside D, capital D half, will have a delta 1 interval attached to it. Right.
Right.
The crux of our proof was basically showing that D1 intersect D half, intersect D1 third, and so on. There is an irrational number inside this intersection. That's the crux of our proof. Right. Okay. In fact, we know that every single thing that is inside this intersection of intervals, well, we know all rationals are inside them, right? And we know that every number inside them will be like a point where the function is continuous.
Yes.
Yeah.
Correct, right. So like what also all these like sets are open. An open set just means it's a union of open intervals. There's a more general definition, but that's good enough. Because like delta 1, they were all open intervals. And we have taken the union of them to get D1. So D1, D half, D1 third, they are all unions of open intervals. So we call them open sets. Okay?
Why is there such a clear distinction made between open and closed intervals? Aren't they like very similar?
When I take a topology class, I'll tell you. Is that a good enough answer? Because we are running out of time. uh, okay. There is like good reasons for this, but I need to point set topology one day. It will happen. Not point, so just topology, whatever. It will be fun. Trust me, guys. It will be fun. Anyway, so what we say is a set S is said to have the G delta property. A set S is said to be G delta if S equal x1 intersect x2, so on, where x1, x2, x3, and so on are open sets. If S can be written as a countable intersection of open sets, then we say S is G delta. Yeah, I'm wrapping up. If anyone wants to leave, you can leave. I'll wrap up in like 5 minutes.
So why don't all the rationals fit into this criteria?
Okay, so like what I am saying here is okay. Let's go back. Let's go back here. Okay. So yeah, I sort of stopped talking here. I was coming to a point. Yeah. So we know D1 intersect D2 intersect D1 third. Whatever this set will be, we know everything inside the set will be a place where F is continuous. Right.
Yes.
In fact, by like a sort of more careful argument, you can show that this, not exactly, but okay, I am like skipping over some details for the sake of time. Like the main content of this class is done. It was to demonstrate that like Q can't be a set of like a set like this. I'm just like yapping for a bit. Bear with me. Uh, so once again, this is sort of not the truth, but you can sort of say that every single point where F is continuous will in fact be like just this intersection. It's not continuous outside of this. Okay?
Mhm.
Not exactly true, but basically. So we say a set is G delta if it's a countable intersection of open intervals. Right.
Yeah, what does countable intersection mean?
Like we take sorry, not intervals, sets, open sets. That means we can take a countably many open sets and like S is the intersection of all of them. Countable just means that like don't take uncountably many. That's weird. But like it doesn't make a difference for real numbers, it doesn't make a difference whether you allow uncountable or not. But just stick to countable.
Okay.
I don't think it should make a difference at least. Yeah. So everyone understands the definition of G delta sets. It just states S is G delta if it's the intersection of countably many open sets, where an open set is a union of open intervals. Right?
Yeah.
So I'll like leave it to you as a sort of exercise to try to prove. But like what we have basically proven above is if S is a set of continuity, that necessarily implies that S must be G delta. Like the basic idea is just what we did here. Like construct D1, D2, D3, D4, and then we know then prove that it can be written as their intersection. I am I'm definitely like hiding some details and they're not important. Once again, I'm just yapping a bit. This is just like if anyone wants to explore further, these are the keywords you should Google. Okay. Uh, the second part, that's like something we have not touched on at all, is if S is G delta, that implies S can be a set of continuity. This is actually like not that hard to prove, and I'll like recommend you guys try it. You just have to find a construction. And yeah. So basically, if you go through like some real analysis or topology, which book? It probably like a real analysis book. They like define G delta sets. They'll prove continuity implies G delta, and then they'll prove that Q isn't G delta. But like that seems like very weird. So instead, I just went in this way to motivate what G delta means. So like I know I've like skipped over some. I don't know. I'm not checked that book. Yeah. I I hope the motivation for like this definition of G delta is clear, like somewhat clear, because I have like skipped over some details. Definitely, like, thank you. But okay. Anyway, I have yapped too much. Okay, forget the G delta part. That's just like you can Google later, or I can like tell you on the Discord if someone wants. The time is almost up. In fact, it's been up for half an hour. Does everyone understand the proof below? Any questions? And then we'll wrap up. I need more water. No, wait. Akshar, Keshav. Okay. If no one has any
Yeah,
questions,
I think,
then
I think I think it's intuitively fine.
yeah, intuitive. And like, no, everything about G delta is like intuitive till now because I didn't prove anything. Everything before that is mostly rigorous. I hope. Like everyone, and yeah, understood. If you have no questions, feel free to leave, which I have like said like 20 times by now. You can ask. I'll stay here for like 5 more minutes for any questions, comments, concerns, blah blah blah, requests. Ask ask me anything, and then we'll end class. Just leave, unless it's
You know,
interactive.
instead of calling the set G delta, you should call it an idiot sandwich.
Alas, I was not alive at the time these sets were discovered, and I did not get to name them. Why do I look? What the hell? Do I look angry, guys? Do I look angry? Poll. Who thinks here I look angry? Whoever thinks I look angry, I'll scold them. Thank you. Thank you for understanding. Anyway, I'll stop recording and continue the nuclear weapons development. Oh, stop sharing.